So this is part 2. You need to remember what we learned in part 1. Okay, that's important. All right. So I've been alluding to this all along. It's just so pretty. It's distracting. If you guys had a window up here, you'd be like gazing out that window because it's just beautiful. Dogs aren't quite sure what to make of it. But. So, all right. Electron configuration, I've been kind of picking on carbon. Like carbon has 6 protons. And if it's neutral, carbon has 6 electrons. So how are those 6 electrons going to be hanging out, configured, based upon the rules that we've been talking about in part 1? And I said that we're going to worry or we're going to focus on electrons as they are in their ground state. Okay. When the other day I said, and I bet some of the homework that you guys turned in are going to kind of reinforce this, I said that for the zip code, you're going to do N, the principal energy quantum number, L, which is the angular momentum, M sub L, which is, I can't remember what that one is, but I know M sub S is spin, okay? I know that the L is the SPDF thing, and this is which box it is. Remember how that works out? And the spin is it up or down, okay? So those are the quantum numbers. So what I meant to do, I'll go ahead and do it. I'm going to go ahead and do this. And this is going to come in handy. When n is equal to 2, we can have a 2s or 2p. When n is equal to 3, I got it, Mrs. Snipes. Oops. Okay. Now, for each of these subshells, we could come up with an n plus L value. Check this out. So, all of the s's, s is equal to 0. This is my L value. P, 1, D, 2, I said E, F, 3. All right? So, for here, n is equal to 1. So, my n plus L value is 1 plus 0. Right? This guy. N is equal to 2. So here I have 2 plus 0, 2. Here I have 2 plus 1, 3. Here I have 3 plus 0, 3. 3 plus 1, 4. 3 plus 2, 5. 4 plus 0, 4. 4 plus 1, 5. 4 plus 2, 6. 4 plus 3, 7. Okay, so those are n plus L values. I mention that because when we start to find homes for electrons, we're going to go with the lowest n plus L value. And I told you the other day that, and maybe I'll just go ahead and do this. I told you that it kind of increases in energy, but I said I had to fix it maybe Friday or Monday. And so let's go ahead and see what that looks like. Change my colors to green. Well, this would be the lowest we got. 1, 2, 3, 4, 5, 4. So I am actually going to show you, and there's a thing called an arrow diagram that's going to make this easier. But this guy's energy actually is right there. Okay, so I have 4, 4, 5, 5, 6, 7, and there's more scrambles, but that's my only scramble I can show you here. I could do a 5, but okay, the lowest n plus L. And electrons go where they can, the lowest energy possible. And it's called the Aufbau method, where we start with the lowest possible energy and we kind of go up from there. Okay. Don't reboot, please. So electrons will be assigned a location with the lowest possible one that's unoccupied, according to all the rules we talked about. Now, when more than one location has the same n plus L value, you're going with the lowest n. So that definitely happens. So like here, we have 2 n plus L values is equal to 3, but this is the lowest n. So they're going to go here first and then here. All right. Aufbau, German for building up. So those 6 electrons that I've been talking about, all right, I'm going to add to this if that's okay with you. So for carbon, first off, an S-type can only have 1 box. So 1 box there, 1 box here, 3 boxes here. So when I'm finding homes for 6 electrons, here they go. Lowest first. 1, 2, opposite spin, 3, 4. And I'll try to have to kind of explain why this is. Now, let's see, I need 2 more, right? And it's called Hund's rule. And actually, these are what we said degenerate. So those are all the same energy. So it's sort of like little kids. If you have a house with multiple rooms, they're going to go into different rooms. They're going to spread out. That's 5, 6. Okay, so that's it. That's electron configuration.
Explain degenerate orbitals again.
Yeah, degenerate orbitals are a set of boxes or orbitals that are at the same energy, the same subshell. Okay. So those are degenerate, and like here, if I had for a D type, I have 5 boxes, and those will all be degenerate. They're all 3D.
So anything more than the S is a degenerate orbital.
It has a potential degenerate orbital. Yep. Yeah, S doesn't, but yeah, P has 3, D has 5, and F has 7. Yep. Yep. So do you see why this is as it is? Check it out. So 4S, they pulled, and they went underneath the 3D. That's exactly what I did. Okay. That's the real deal. Okay, I'm not sure what this is for. It's been a while since I studied this, but the way it works is if you have an atom that only has 1 electron around it, you're like, well, when would that be? Hydrogen? Or it could be helium that lost 1 electron. But if there's only 1 electron, then these kind of multiple L values all kind of come together, and they're all lined up like that. They split when you have more than 1 electron. Well, that's pretty much everything, right? So I'm going to talk you through 2 ways of showing how electrons are configured. So this would be the 6 electrons around a carbon. And the awesome thing, so what's after carbon? Nitrogen? I just love this. They just have such a rhythm to it. And maybe it's the musician in me. I'm like, that just flows. So that's carbon. So for nitrogen, you need 7 electrons. Guess what? That's it. Okay. So there's 2 ways to describe how electrons are configured. This I call the hand cramp because it's a lot of, my boxes get kind of ugly. The boxes represent the orbitals. The arrows represent the electrons, okay? So this is box and arrow notation. I'm going to show you another type called spectroscopic notation coming up. So we all okay with this? So that up and down arrow, remember how that works? That quantum number is +1/2. It's up, -1/2, it's down. Okay. So, you guys have like little boxes to fill these in? Okay, good. So 1 electron around hydrogen, looks like that. 2 electrons around helium. So one of the rules is that it will, there are some exceptions, and I'll kind of, yeah, there are some exceptions, and we'll get to those on Monday. But one of the rules is that they completely fill up a subshell, degenerate orbitals, before they go on to the next subshell. So lithium, we're excited. We get to pick up a 3rd electron, so it looks like this. Okay. And for beryllium, where will that 4th electron go? Yep, it'll definitely buddy up in the 2s. We have to show opposite spins. You got it. So after beryllium, you're looking at, boron. All right, here we go. Where's the next electron going to go for boron? The first 2p, exactly. So after boron, that's 5 electrons, atomic number 5 element. What about carbon? Where did I say that last electron goes? Yeah, if possible, it scoots over. Okay, and I think the next slide shows one of the terms that you might see on your Unit 4 exam. It's called Hund's rule. There's 2 things. Actually, we already covered the other thing, and sometimes I get Hoone's rule mixed up with what we talked about, Pauli's exclusion principle. Pauli's exclusion principle that said that you can have within the same atom, you can't have any electron that has the exact same set of 4 quantum numbers. That's Pauli's exclusion principle. Hoone's rule is the spread out rule. Like if you have kids, okay, they're going to do kind of what we do with carbon, where we're going to go ahead and start filling the degenerate orbital. All right, notice that they're going to have the same spin. So when I talk about disallowed or maybe a higher energy, I'll show you what a higher energy would be, because sometimes you run into this on it's a subtle thing. But I'm going to go back to carbon. That was nitrogen, now we're at carbon. What would be more energy or disallowed would be this. You're like, are you serious, Mrs. Snipes? Okay, but hey, see the difference? It's not because you've got the same spin. Okay. And the way this works is paramagnetism actually has to do with unpaired electrons, so it is a player. And the nuclear magnetic resonance that we talked about, unpaired electrons. So here we go. Nitrogen, so where do you think that electron beyond carbon's going to go, or nitrogen, carbon's going to go? Where's the last one going to go? Yep, the last one. Okay, so we got 2, 4, 5, 6, 7. 7 electrons, atomic number 7. See how that works? Okay, so oxygen, we're going to do this. Now, but already kind of, the fact you see no more boxes up there kind of suggests we're not going to go on to the next subshell. We're going to go ahead and buddy up like you would do if you have kids. You're like, dude, we got another kid. Where are they going to go? Well, they have to buddy up with you. Okay? And then fluorine follows that same pattern where we completely fill the first subshell, completely fill the second subshell. We're going to completely fill the first subshell of the 2p, and now we actually got to fill the second subshell of the 2p. Now neon, we're at the end of a row, end of a period, and it's very exciting time. So some of you guys remember actually neon, argon, krypton, xenon, radon, and helium they're rare gases. They have a rare gas configuration. They have a rare gas electron configuration. So here we go. It gets really exciting. So if you ever come up against, this is generally called, it's generically called N, where N is N is N. So N are these numbers. If you have an NS2, 2 electrons, and actually I'm kind of introducing you to the other type of configuration notation. This is called the spectroscopic notation. NP6. Okay, NS2, where N is equal to 2 electrons, NP6. 6 electrons. That's what we call a rare gas configuration. And that's a big, hairy deal. It's very exciting. So that's actually a good transition to, we're not ready yet, but that's a good transition to the other way to say how electrons are configured. What you do is instead of writing the boxes, you don't write the boxes at all. You write the subshell. So I have 1s up here. Oh, I lost my gold. 1s is the subshell where that electron is in. And the superscript 1 of the s is saying how many electrons there are. Really? It'll show up. Huh. Does this one work? Nope. Okay. So we're going to do those same elements. I'm going to show you. This is like the opposite of box and arrow notation. So hydrogen has 1 electron. Helium has 2 electrons. So instead of using a box to show electrons, show 2 electrons, what we're going to do is we're going to put a little superscript 2 associated with this 1s. Now, when you're doing this sort of notation, what I've seen students in the past is you don't want to get your superscript too big. Your superscript is supposed to be a superscript, which is kind of small. The thing, the n is big. So 2s is the n and the l. And the superscript 2 means how many electrons. All right, here's lithium. 1s2, 2s1. And that's how you'll hear me say it. 1s2, pause, 2s, that's the subshell. 1 is how many is in there. And then this is, you might imagine, if we want to know how many electrons we've accounted for, all we got to do is add superscripts. 4 electrons, 4 electrons, 1s2, 2s2. 5 electrons, 1s2, 2s2, 2p1. I feel like I'm playing bingo, like calling out little bingos. So again, you're like, boron, how many electrons are we talking about? Well, 2 plus 2 plus 1, we're talking about 5. Then after boron, we have carbon, 1s2, 2s2, and 2p2. And if you're like me, here's where you start scratching your head like now this actually has less information than the box and arrow because we can't show those 2 electrons in the 2p2, we can't show them in different orbitals. You just got to know that. After carbon, we have nitrogen, so 1s2, 2s2, 2p3. Then we go to oxygen, 1s2, 2s2, 2p4. And do you see maybe where I mentioned that what we talked about in part 1 is important now because we can't have a 2s5. Like, dude, you can't put 5 electrons in a 2s. Why? Because it's an s, it only has 1 box. Okay, but we can put, what, 6 electrons in a p, so let's keep going. So, fluorine, 1s2, 2s2, 2p5. And then neon, 1s2, 2s2, 2p6. And you can see when I mentioned this rare gas configuration, that's whatever, actually just your, well, I'll talk about valence electrons coming up. Whatever your valence electrons are, that's, can you see where this 8, we got 8 because we have ns2, that's 2 plus np6, so 2 plus 6 is 8. Here in this part, we're going to talk about how like water sticks together, how those 3 atoms make water. And there's going to be this kind of trend of 8, octet going on. So this is our octet. All right, what else we got? Well, this whole thing, this being where I kind of showed you how we come up with an n plus L value for each subshell, and then we re-scramble them based upon increasing n plus L value. That's a pain in the butt, okay? Instead of that, there's 2 ways to kind of work around that. I'll show you the other one on Monday. This one is called the arrow diagram. So what you do, and I don't think I'm going to recreate it here, but it's important because actually if I was taking a test on this, like you guys are going to be doing in a few weeks, I would write the arrow diagram. I know it's cheesy, but I would write the arrow diagram on my test and use it. I'll show you how it works. So of course 1s means n is equal to 1 and an s-type orbital. For n is equal to 2, we have 2s2p, n is equal to 3, 3s3p, 3d. If you're doing an arrow diagram, you want to make sure your columns line up. N is equal to 4, we pick up the f-type. So 4s, 4p, 4d, 4f. And actually, we do all the way to 7. And I can't remember how I do this. I think I go ahead. I think, see the stuff that's grayed out? Remember that we, since we're only worried about electrons in their ground state, we're not going to have to mess with G's, H's, and I's. So I think where it's bolded, that's where I stop. Okay, so they call it an arrow diagram because now we make these diagonal arrows. And if you've made your columns nice and neat, then these diagonal arrows go just great. Each diagonal arrow represents an n plus L value. So 1s, n plus L value is 1. The next diagonal, well, there's only one thing, okay, 2s. Now, the next diagonal, it's got to go through these two guys, right? And that's where you're going to see it. It's going to start at the top, go 2p, 3s, diagonal. The next one's going to go 3p, 4s. Why? Because they have the same n plus L value. 3p, 4s. So when you're loading electrons, though, you're going to start at the top of the diagonal. Now this gets exciting. Check this out. Now we pick up 3 subshells that have the same n plus L value, which must be, what do I say, 3d5. So my point here, and we're going to do some examples, is we are going to start at the top of the arrow, go down. Top of the arrow, go down, top of the arrow, go down. And the off-bow method is to build up. Okay? So these are increasing n plus L values. And your book or OpenStack uses it this way, but I like mine. It's less confusing. So let's do one. And I actually a while back bought these dice that you can roll them and they can give you like big numbers. And so and I looked them up, and then so we might just do a roll one, and then that's going to be how many protons, that's going to be the atomic number, and then we're going to have to find that home for that many electrons. That's fun. But potassium is atomic number 19, 19 protons, 19 electrons. So here we go, and this is kind of show you kind of where I'm going to start. I'm going to start with the 1s. And how many electrons can I accommodate? 2. Do I need to accommodate 2? Yes, I'm on my way to 19. Then I go to the second diagonal. So 1s2 is the first one. The second diagonal, 2s2. Okay. So to try to keep your eye on the goal, you don't want to go over 19. We've got 4 now, headed up. Now I'm going to go on to my next diagonal, start at the top of the diagonal, which is 2p. I can shove 6 electrons in there, and I'm going to completely fill it. 2p6. Okay. 2p6. And now I'm at what? 2 plus 2 plus 6. I'm at 10. 10 electrons. And that actually would be neon. So now I'm going to go to 3s. 3s2. So I've got 12 on my way to 19. What comes after 3s? 3p. And how many am I going to put there? 6, yep. So now I'm at 10 plus 2 plus 6, now I'm at 18. All right. And actually, we're at an NS2NP6. So we are at a rare gas. We're at 18. Would you buy argon? I would. So we're argon right there. So I'll need one more electron. Where's it going to go? 4s. So I end up with a 4s1, even though it could have 2. I don't have 2 to give it. Yeah. And that's it. But notice this is a really good example. What I see on students, unfortunately, and I can see why, is we just want to kind of fill it, just go to la-di-da-di-da across like this. So you guys told me it goes in the 4s, but sometimes students will think, well, it'll be 3d1. No, that's not right, because 3d actually is a higher n plus L value than 4s. All right. So that was in what we call the order of filling. Oh, sorry. That was the order of filling. All right, one more. 40 electrons. You're like, what? So the first is going to actually, we could kind of do all the way up to argon. It's going to be the same. So 1s2, 2s2, 2p6. And then 3s2, 3p6, that's up to argon, that's 18. And then you told me we're going to 4s, but we need to fill it, so 4s2. Now where do we go, and how many electrons? 3d10, I agree, we're at the top of that next arrow. 3d, and 3d10 will get us, let's see, 12 plus 18, you're still at, what, only 30? So we need 10 more. So where we go next? 4p, yep, and since we need 10, we're gonna go ahead and fill it. Yep. So we must be at another rare gas. And what rare gas that be? Krypton. So we're at 36, we need 4 more, so now where do we go? Yep, now we go to 5s. Yep. And how many electrons? 5s2, I'm liking it. Now where do we go? 4d, and how many electrons? 2. You got it. That's it, man. Yep. So that's 40 electrons of zirconium as they are in their ground state. So this is what we call the order of filling, and sometimes we unscramble it. This is, by the way, on a test, this is the way I would leave it. But you can unscramble this in order of increasing n, okay? And it would look like this, where basically we're going to have to pull out some things. So, do you guys have this one already? Okay, good. So can you see where it's the same configuration, but now we're just increasing the order of principal energy level n of the subshell. Yeah, that's a good place to stop. So we'll pick up with iodine and finish this part on Monday. Gosh, week went fast.